Okay, welcome back. So any questions before we get started? So if not, let me... Okay, so last time we went into grouped data, so finding values, means, and such within group data. Find the mean within a group data, and the group data just means that this is all data that's already been summarized for you, but you don't have access to the original data. So this is for figuring out population mean, and these are just estimates of the population mean. It's not going to give you the precise value because you need the original data to find the precise value. But notice that whether you're looking at the sample or a population mean, the calculation is essentially the same. So you're going to take x1, which is, and so xi we took as the representative value for all the values within a particular class. And in this case, we settle on the midpoint. We take that midpoint, multiply it by the frequency, the height of that graph, or the bar that the class represents. And then we go through all of the classes like that. There's a couple of things to be noted here is that the sum of all these values in the denominator, that should equal n, because remember, that's how you figure out the value of the mean. Take all the sums of the data and then divide it by the number of data that you have. So population mean, the sums of Fi should equal the population size. If you're talking about a sample, sum of Fi is the sample size. And then went to a example of this, and then we looked at each of the classes. I only included the first class. Normally, if the initial class is 0, then it shouldn't be included, but for some reason the author included it, so I went ahead and called it I as 1, because that's what the I is to represent. What class is that? 1 to 5 is the first class with a size, and notice that 1 plus 5 is 6, divided by 2 is 3, so we're just looking at the midpoints of each of these classes and then multiplying the 130 times 3, that gives you 390. The 230 times 13 gives you 2,990. So the sum of the FIs, that's 1,000. The sum of the XIs times FIs, 14,250. Work out your mean. So you get 14.25. So the mean hours of studying per week is approximately 14.3 hours. Since all of these classifications, all these classes are, 1 to 5, 6 to 10, whole numbers, we really don't know what the original data was, but it's possible that they were all whole numbers. The mean is rounded to the next position past the whole numbers, so the 10th place, so 14.3. And that brings us back to where we left off. Compute the weighted mean. Now this is pretty much nothing more than what we've looked at with the grouped mean. The weighted mean is a variable found by multiplying each of the values by its corresponding weight, adding the products, and dividing this by the sum of the weights. It can be expressed during using the following formula. Hopefully you notice that there's a similarity between the calculating the mean for the grouped data. In fact, it's pretty much the same thing. In this case, the frequency is the weight of each data value. But there are other uses for it. So yeah, the group mean estimate for this is that. This is nothing more than the weighted mean, where the weight for each observation, xi is the frequency. There are other uses for the weighted mean. In college, we use it to determine the GPA. An A in a 4-hour stats course, a B in a 3-hour sociology course, an A in her 3-hour psychology course, a C in her 5-hour computer programming course, and an A in her 1-hour drama course. And when you work out the mean, so A gets translated to 4, B converts to 3, a C converts to 2, and then the weights is the hours for each class. Grade point average is a common example of this. Approximate the standard deviation from group data. If you have the mean, it is often nice to have the standard deviation to go with it. So to approximate standard deviation, a variable from a frequency distribution, notice that we are harping on frequency distribution. None of this is going to work with relative frequency. So population standard deviation is given by this, and notice we still need the population mean that we alluded to earlier, or we covered earlier. So mean required beforehand. Sample standard deviation. So again, you still need to figure out the sample or the estimated sample mean. Notice with the population standard deviation, the numerator was divided by the capital N, the population size. Here we have the sum of all the frequencies, so which is the population size. Over here for the sample mean, the denominator had this -1 included, so this part still remains in place. We just have this part representing the sample size. So really the formula hasn't changed. It's just what is needed to find that value that's been tweaked a little bit to incorporate this whole idea of grouped data. So again, xi, the midpoint value of the ith class, fi is the frequency of the ith class. There is an algebraic equivalent to this, or a computational equivalent, that does not require the mean. Here's the computational equivalent for the population standard deviation, and here it is for the sample standard deviation. So no means required. The only thing required is to have this xi squared, and once you've taken the sum of the whoops, this is missing an fi. Here you're going to take the square of the xi's, multiply it by fi, and then you're going to take the sum of all those products. Here you're going to take xi times fi, take the sum of all of that, and then square it. Example 3, approximating the standard deviation from a relative frequency distribution. We're going to look back at a previous example. In this case, looking back at earlier example regarding 50 parking tickets. Here are all the classes that were involved. Here's the midpoint for each of the classes, and then we had a frequency count. The original way to do it was to first figure out the sample mean. In that case, they turned out to be 182.5. Take the 62.5, subtract 182.5, and that will give you this negative 120. You're going to square that 120 and then multiply it by 1. 120 squared and then multiply it by 1. And that gives you these 14,400. And you can do that for all of these rows. So in the end, you have a sum of the frequencies, which is 50. You have the sum of all of these values here, 14,750. Plug it into the formula and then round it off to the nearest, since all of these were in pennies or the hundredths place of $1. do we need to calculate these by hand or use StatCrunch to do it for us? So again, you can use StatCrunch or you can use Excel. Throughout this whole class, I'm not going to limit anyone to like, oh, you have to do it by calculator or something along that line. That could be done during the homework, but holy cow, if it's done during an exam, there's just not enough time to do it. So yeah, I'm going to try to avoid those kinds of questions on exams. You can do it with Excel, and I'll show you how to do it in Excel when we're done with section 3 here. Here is the same thing that we can, same classes, same midpoints, same frequencies, but now you have the xi, fi, xi squared, and so this is the elements for doing it the computational way. Xi, fi is the second column times the third column, that gives you the fourth column. You take the second column, you square it, that gives you the fifth column. And then you take this fifth column times this third column, that gives you this, sixth column. Add up all these numbers, so the sum of the frequencies, 50, the sum of the xi's, fi's, 9,125, the sum of the xi squareds times fi, 1,800,000. Plug them all into the formula. So here, this is a sample. So we're going to use the sample formula. So this is replaced with this. The inside here is replaced with that. And then these here, they are replaced with 50. Calculate it all out, and you get this approximate standard deviation of $54.16.3. Since all of the values were in or hundredths of a dollar, the rounding will be, once you've figured out the calculation, it'll be rounded to the next figure over. So tenths of a penny or thousandths of a dollar, hence the 54.163. That will be the end of that. Here's the first example. I dropped out the item dealing with the zero frequency. So frequency there. Xi, there are two ways of dealing with the Xi's, the midpoints. If your classes are represented in this way from one whole number to another whole number, then the midpoints here, you can calculate by saying, okay, so equals, we have to do parentheses. So the addition is counted together. The A2 plus the C2, close parentheses, and then divided by 2, and that gives you the 3. So now we'll find the xi times fi, since that was one of the things that the computational formula looked for. Hit equals, move it over to the fi, and then you're going to hit asterisk for multiplication, and then put over the midpoint. Now remember, multiplication is commutative, meaning 3 times 2 is the same as 2 times 3. These references of C2, D2 doesn't have to exactly match the order of xi times fi. So you get 390. You don't have to copy this for every column. What you could do is highlight both of these cells. And if you notice in the lower right-hand corner of the highlighted cells, there is a exaggerated corner. If I put my mouse over the frame of what's been highlighted, I get a little plus. But if I put the cursor over that exaggerated corner, I now get a plus, but no arrows at the end, which means, oh, you want to copy this, what's being highlighted. It's like, yes, I want to do that. So I hold the mouse click down, I drag the mouse down to the last row, I release the mouse, and now it has copied this arrangement for each of the rows. The only thing that's been adjusted is the row number. If you look up here in the field, so you see C2 times D2, but if I move it to the one below, now it's C3 times D3, because we're looking at the third row of the C column and D column. So that's how you can do the copying all those things without having to type it all in. I need the sum of the frequency, so I'll go to the bottom. Actually, I'll type in sum here. Go to the bottom and auto sum. So in the upper right corner, you have this auto sum, which tells Excel to, oh, you want me to sum up all the numbers above this particular cell? Yes. Okay, I'll stop until I hit some words that are not numbers. So there's that. There's that. So we get 14,250. There are other things that we need. There was one other thing that we needed. So xi squared times fi. So for this, I'm going to go equals and go to the xi column, introduce a caret, which means to the power of. Well, to the power of what? Oh, it's to the power of 2. And again, multiply it by the frequency count, which was this value here, and we get this. So it's going to take the square of 3, which is 9, multiply it by 130, so that gives you 1,170. I'm going to copy all of that to the rest of the rows, and underneath it, I'm going to calculate the sum, which gives me this. Now, you can take these values here and take it to the calculator because you have the formula, which in this case will be the bottom formula. So what would that look like? So here's the formula. So 268,750 minus 14,250, that's going to be squared over 1,000, all divided by 1,000 minus 1. So when you look at it from a calendar, first we will take the 14,250, we'll square it, we'll divide it by 1,000. Here, we want to subtract this from the 268,000. So what I'll do is change the sign. So instead of keeping it positive, I'm going to make it negative sign and then add to that the 268,750. So that gives me this number. And then the 1,000 minus 1, that's 999. So we'll take that result divided by 999 and it gives us this. And then that result, we're going to take the square root. So we get 8.108. We're assuming all the values were in whole numbers, 8.1088, et cetera, et cetera, et cetera. Assuming that all the original data was in whole numbers, we round it off to the 10th place. So this will be our standard deviation. Technically, we could do this within Excel too. It would require having to follow the formula as best as possible. This is what it would look like. So standard deviation. Now, Excel doesn't have a standard deviation function for group data. That's why it has to be done by hand. So equals. The whole thing was in square root. We'll do the square root. So that will introduce the square root. The square root of what? So this is going to require a little bit of conceptualization. So the numerator, we're going to first do the numerator. So the numerator will introduce a second parentheses. The numerator involves taking this number, the sum of the xi squares, minus, and then it required, the square of this number. So that number, we're going to square it and then divide it by this number here. And that finishes it for the numerator. Now, by doing it this way, the division is only going to apply to this part of the equation. Now we'll introduce dividing by the denominator. What's the denominator? We need to introduce a new parentheses for the denominator because there's more than one part to it. That, again, minus 1. If the minus 1 was not there, we could get away with just divide by C9. But because of the minus 1, we have to throw it all in parentheses. Now, you could go through and say, oh, every time, now could go through and start throwing in closed parentheses, and notice that every time I throw in a closed parentheses, it's going to highlight its associated parentheses on the other side, so you can kind of check for yourself, oh, do I have enough parentheses? And in this case, yes, I do. There's our 8.108838, et cetera, et cetera, et cetera. One advantage to doing it this way is because if you have homework and it's telling you, well, what if the frequency had for the fifth classification, so the fifth one was 110. So you can punch in 110 and everything will be recalculated. So you don't have to worry about calculating a new standard deviation. Excel does it all for you. As long as the formulas are in place, everything that has a formula that includes this value here will be adjusted for that new value. Can you show how to do that in StatCrunch, please, please, please? I guess it'll be good to do that because yeah, not everyone would have StatCrunch available. Well, let me bring up StatCrunch. I have to correct myself. Let me bring up StatCrunch. Here's the same data. Here you have, and notice that the classifications are given in, with Excel, I had one column for a lower bound, another column for the upper bound. Here, the classifications are all together. So 1 through 5, 6 through 10, 11 through 15, 16 through 20, et cetera, et cetera, et cetera. So these are the classifications, and here's the corresponding count. Now, if you go to Stat, if you go to Summary, notice down here, there's a thing called Grouped Binned Data. Click on that, and it gives you this. So here you're going to tell StatCrunch the bins, the classifications, that is, they are in var1, the first variable. So if you look over here, var1 is where the classifications are. The count is in var2. Here, you're asked, what is the midpoints defined by? In this case, we want it to be the average of the limits. That is the upper bound and lower bound. But you can also do it by the consecutive lower limits. This would only be done if you're dealing with continuous variable. With the last example in section 3, we had the 50 up to 74.99. That would be an example where you would use consecutive lower limits. But here, we're dealing with whole numbers. We'll just deal the midpoint being defined by the limit themselves. Over here, down here, we get to see n, the sample size, the mean, the variance, the standard deviation, median, range. So we have all of these values here. Some we're not going to look at. The important thing is to verify, oh yes, I do want the standard deviation here. Hit compute and you get this table. Notice the n is 1,000, which is what it should be. The mean is 14.25, and there's your standard deviation of 8.108, et cetera, et cetera, et cetera. This is group data, so all of these are just estimates. Just like this median value is an estimate of what the true median is. Just like the range is an estimate of the true range. The minimum, the maximum, the Q1, Q3, those are all estimates of what. That's how you would do it in StatCrunch, which seems much quicker than just make sure that when you're doing it in StatCrunch, make sure that your classifications are in this fashion. So lower bound dash upper bound. And if you need to, if you're dealing with discrete values, like in this case, you're going to use limits. If you're going to deal with continuous variables, you would use consecutive lower limits. So yes, you're welcome. I'm glad I was able to correct that. So determine and interpret z-scores. By the way, z-scores is going to pop up later on in a major way, so don't overlook this. Percentiles, interpret quartiles, interquartile range, and set of data for outlier. Okay, so determine and interpret z-scores. What is a z-score? So the z-score represents the distance that a data value is from the mean, but in the terms of standard deviations. So we're not just going to look at the difference between a data, how far a data is from the mean. We're going to state that in terms of standard deviations. We find it by subtracting the mean from the data value and dividing this result by the standard deviation. So there is both a population and sample z-score. So for the population z-score is determined by this. The sample z-scores is determined by this. Notice that the calculations are the same. It's just the symbols that are different. These are equivalent. S for sample, sigma for population. These are the same idea as well. Mu for population, X bar for sample. Note the z-score is unitless. So the data may have units like pounds, inches, seconds, whatever. But once you work through all this, the units are all taken away. And also, the z-scores themselves end up having a mean of 0 and a standard deviation of 1. So this is a way to convert your data from what it is now into a converted system that has the same properties, but now it has a mean of 0 and a standard deviation of 1. It's almost like converting from kilograms to pounds or from meters to feet. It's just a means of conversion into a new system that keeps the original properties of how the data look into a new system where the mean is 0 and the standard deviation is 1. And yes, that will become extremely handy when we get to chapter 7. But it also allows you to do certain other things. So example 1, comparing z-scores to determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run-producing season. Red Sox, you see it scored 876 runs and play in the American League where the mean number of runs was 731.2 and the standard deviation was 72.6 runs. The Dodgers, they have a mean of, they scored a mean 804 runs in the current season, and looking through the history of all the seasons, its mean was 710.8 and the standard deviation was 60.2. So we're looking at the current. That's the 876 for Red Sox, 844 compared to the historical record. So that's where you get the mean and the standard deviation. And if we look at all of that, which one had the better run, the Red Sox or the Dodgers? Red Sox, we will calculate z-score for it. The 876 minus the 732.2 divided by the 72.6, and we get a z-score of 1.99. The Dodgers, same thing. 804 minus 710 divided by 60.2 to give you a z-score of 1.55. So the Red Sox had a production run of almost 2 standard deviations above the mean, while the Dodgers had a production run of roughly 1.5 standard deviations from the mean. Therefore, the Red Sox had a relatively better year at scoring runs than the Dodgers. You can kind of see it if you look at the Red Sox, 876 versus 731 for an average, 140 more. Dodgers, 804. So this is like roughly 90 runs over the average, and then divided by a standard deviation. So you can kind of see that the Red Sox had a better, and the relatively is dealing with, we're comparing these two together. We're not talking about the Red Sox and the entire league it's from, or the Dodgers and the entire league it's from. We're just comparing these two together. Percentile. You've probably come across this before. The kth percentile, denoted by pk, is a set of data is a value such k% of the observations are less than or equal to the value of pk. So here's a range of all the values. These are the P1 is for the position of P of 1%. The P2 is second percentile. P3, the third percentile. P10, the 10th percentile. P98, the 98th percentile. Between the smallest value and P1, that's the bottom 1%. Between the smallest value and P10, that's the bottom 10%. Between the largest value and P99, that's the top 1%. Between the largest value and P95, that's going to be the top 5%. Jennifer just received the results of her SAT exam. Her SAT math score was 600, is in the 74th percentile. What does this mean? Remember, the kth percentile, in this case the 74th, means that k% of the observations are less than or equal to the observation. So being at the 74th percentile means 74% of the math scores are less than or equal to 600. But it also means that 26% of the scores were greater than. So 26% of the students who took the exam scored better than Jennifer. Quartiles. I may have or may not have heard of these. So quartiles divide the data into fourths or 4 equal parts. Hence quartiles, quarters, quartile, quarter, quartile, quarter. So the first quartile, denoted as Q1, divides the bottom 25% of the data from the top 75%. Therefore, the first quartile is equivalent to the 25th percentile. So hopefully that part makes sense. 25th percentile, bottom 25%. The second quartile divides the bottom 50% of the data from the top 50%. So it is a 50th percentile, which is equivalent to the median. So Q2 is essentially the median. Third quartile, the same as the first quartile, but it cuts off the bottom 75% from the top 75%. This is nothing more than P75. So here's another view of the 3 quartiles, smallest data to largest data, and you have Q1, Q2, breaking it up into 25 equal parts. When you do the actual calculations, it won't be exactly 25%. I'll show you why. Finding quartiles. So like before, like with the median, arrange the data into ascending order. Smallest to largest. Determine the median M, and this will be your second quartile. Once you find the median, that's going to break it up into 2 equal parts. Divide the data set into 2 halves, the observations below the median and the observations above the median. The first quartile is the median of the bottom half of the data, while the third quartile is the median of the top half of the data. So here's all your data. You're going to find the median, and this median will essentially become your Q2. But it also separates this into 2 smaller sets of data, and you're going to repeat this process for each of these 2 sets. So find the middle, so that will be Q1. And then find the median here, and that will be Q3. Finding and interpreting quartile, the Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured individual's vehicle. The data in the next slide represents a random sample of 18 collision average claims based on data obtained from the Highway Loss Data Institute. Find and interpret the first, second, and third quartiles for collision coverage claims. So here's the data. So step 1, so we're going to take the data and put in ascending order. Start with 180 and then put in the next highest, then the next highest, then the next highest, et cetera, up to 21,147. Now there are 18 observations, even number. So the median of all these 18 observations is going to be the mean of the 9th and 10th observation. So the 9th is this one, the 10th is this one. And if we take the average of these two, we get is 1805. So that's the median. That's the first round of medians. So that is going to be our Q2. Because of that, we can now split the data into two groups. So we'll look at the first group. The first group is going to be all the data that is smaller than 1805. So we have all of these. And then we find the median of these sets. So there's 9 observations. So that means the middle one is the 5th observation, which is this bolded 735. So Q1 is the 5th observation, $735. But we also have to deal with the top half. So here's all the data above 1805, and the middle one is going to, or the median of this set is going to be this 4668. So Q3 is going to be 4,668. So all the 3 quartiles are these. What does that mean? Don't read too much into it. This is not quantum theory or anything like that. 25 of the collision claims are less than or equal to 735. That's the least that you can say. And 75% of the collisions are greater than 735. Stop at that point. That's all that's being asked about. Q2, 50% of the collisions claims are less than or equal to 1,805, the second quarter, and 50% of the collisions are greater than 1805. And similar for the third quartile. Not much to be said about it. We'll look at what's called the interquartile range. So the interquartile range, or IQR for short, is the range of the middle 50% of observations in the data set. That is, the IQR is the difference between the third and first quartiles and is found using this formula. Notice that there's some similarity to just the simple range. The range was the maximum value minus the minimum value. Here we're talking about the interquartile range. So now we're going to replace the maximum value with the maximum quartile. So this is just going to be Q3 minus the minimum value, or in this case, the minimum quartile, Q1, and then subtraction. So this would be like a second cousin to the range, in a manner of speaking. And interpreting the interquartile range, determine the interquartile for the collision claim data. So the previous example that we're looking at, Q1 and Q3 were these values, and if we take the difference, that's going to be 3,933. So that is the range of the middle 50%. This is always the case. The middle 50% of the observations is 3,933. So the middle 50% covers a range of $3,933. The simple range covers 100% of the data. The interquartile range covers 50% of the data. So this is kind of a rule of thumb. If you have data that's symmetric, the better measure of central tendency will be the mean, and the measures of dispersion will be the standard deviation. On the other hand, if you're dealing with skewed left or skewed right, so remember, skewed left means that all the data or the graph is kind of empty on the left. So it kind of looks like this. So all of these values on the left are extreme values, and the mean will always gravitate towards the extreme values. Be nice for the mean to, hang around where the majority of the data is, but it doesn't do that very well. So it'll tend to gravitate towards the extreme values. So it's not a very good measure if you're dealing with skewed data. The better one for that would be the median. Standard deviation, so that works best, or that often works better with symmetric data. But if you have one that is skewed either left or right, then the interquartile range would be the better way to go in that case as a measure of dispersion. So checking for outliers. There are different ways of doing it, but the only way that this book, that the author covers, is using quartiles. What are outliers? So if you have data, so here's our number line, you've collected data and they all tend to clump in a certain area. So most of data. But every now and then you may end up data that is like way outside the group. Now it'd be like going to a meeting someplace and everyone is roughly the same height, but a 7-foot person enters the room and it's like, oh, wow, that's a tall person. That person would be an outlier. Unless, you have a meeting of 7-foot people and all of a sudden a 5-foot person enters a room. Oh, okay, that person's not as high. The 5-foot person will be an outlier. So an outlier is any data that strays away from where the majority of the data tends to lie. And so what we're going to do is try to figure out a way of highlighting those. Now, every now and then, it's possible that when you're measuring the data that these outliers are errors that just crept in. If you do get outliers, the best thing to do is go back. Hey, did I measure this wrong? Maybe the 37 became a 73, the accidental reversing of digits or something like that. It's possible that they may be errors, but not all the time. It's like, holy cow, I really didn't calculate this wrong. It really is that value. Well, okay, that's the way it is. So there are different ways of detecting outliers. This one is going to be involving the IQR, the interquartile range. So first, we're going to determine the first and third quartiles of the data. Compute the interquartile range. Determine the fence. So fences serve as cutoff points for determining outliers. So for the lower fence, it's going to be Q1 minus 1.5 IQR, Q3 plus 1.5 times IQR. Notice it's the same thing. The only difference is for the lower fence, we're dealing with Q1 minus, and then upper fence Q3 plus. Otherwise, the rest is the same. If a data value is less than the lower fence or greater than the upper fence, it is considered an outlier. So sample 3 revisited. So we'll go back to the insurance, check the collision claim data for outliers. So as a reminder, the first and third quartiles were 735 and 4,668. The interquartile range was 3,993. So the fences are going to be these. So the lower fence, Q1 minus 1.5 IQR. So 735 minus 1.5 times 3,933, which gives you negative 5,000. The upper fence, Q3 plus, so we get 4668 plus 1.5 times 3,933, so roughly 10,500. Now, if we look at all the data, which ones lie outside these fences? Now, they're all positive, so there's nothing lower than the lower fence. On the other hand, if you look at the upper fence, this 10,034 really gets close, but it's still not enough. But this 21,000, yeah, that's more than double this upper fence. So step 4, there are no observations below the lower fence. However, there is an observation above the upper fence. The claim of 21,147 is an outlier. There may be one outlier. There may be dozens of outliers. If you're dealing with a large set of data, you may have a few that could be classified as outliers. That's the end of 5-number summary and box plots. Objectives: compute the 5-number summary and draw and interpret box plots. So we'll first look at the 5-number summary. So the 5-number summary is a set of data that consists of the smallest data value, the 3 quartiles, and the largest data summary. Remembering that Q2 is also the median, we organize the 5-number summary as follows. So the 5-number summary is the minimum, the Q1, the median, Q3, and the maximum. So the data below shows finishing times in the men's 60 to 64-year-old age group of a 5-kilometer race. Determine the 5-number summary of the data. They're in minutes. Okay, so all seconds were converted to decimal minutes. First, we write the data in ascending order. So we go here. So the smallest up to the largest, the 54.63. 5-number summary. So if we were put it in StatCrunch, we get this. And we're not interested in all the results. We're only interested in the results that are in bold. So minimum, Q1, median, Q3, and maximum. So this is the 5-number summary. Now, given this data, we can draw what's called a box plot. And there are 2 ways to deal with the box plot. One that highlights outliers and one that doesn't highlight outliers. This author in this section has decided to deal with ones that do highlight outliers, but it's not always the case. If you do choose not to highlight outliers, well, let me get to this. So drawing a box plot. First, determine the upper and lower fences. Here are the formulas for that. Draw a number line long enough to include, so it's kind of a graph, if you will, but not normal kind of graph. Including minimum and maximum values, insert the vertical lines at Q1, M, and Q3, and close these vertical lines in a box. These is referring to these Q1, M, and M3. Draw the box plot. So drawing a box plot, label the upper and lower fences. Draw a line from Q1 to the smallest value that is larger than the lower fence. Then draw a line from Q3 to the largest value that is smaller than the upper fence. These lines are called whiskers. Any data less than the lower fence or greater than the upper fence are outliers and are marked with an asterisk or something. Going back to the running data, as a reminder, the table shows the finishing times in minutes. Here's the data. These are going to be the Q1, median, and Q3. So there's 21 pieces of data. This should read 30.35. So that means that the Q1 should be the median of the first 10 pieces of data. So there's 10 of them, so it's going to be the midpoint between the 5th and 6th data. So it should be the median, the midpoint between these two. Q3 will be the median of these two. Okay, Q1 is okay. Yeah, this should have been 35.11. So we'll stay with a mistaken Q3 because I don't want to recalculate everything that comes after this. Lower fence, like what we did before, so it comes out to be 9.29. Upper fence, 54.101. And there we have it. So this box here, that is the middle 50% of the data. This first vertical line is Q1. This second vertical line is the median. The third vertical line is Q3. And this is the middle 50% of data. The lower fence would have come out to 9.29, somewhere around here. So I'm represented by a dotted line. The 54 is the upper fence. So that came out to roughly here. So now if we look back at the data, the minimum value was 19.95, maximum value 54.63. So this left whisker here goes out from Q1 down to the smallest value that was larger than the lower fence. Well, coincidentally, that happened to be the smallest data value available. The minimum was automatically satisfied that condition. For the upper fence, 54.0, we're looking for the largest value beyond Q3 that is smaller than the upper fence. And that happened to be this value here, which is 41.42. So anything outside the lower and upper fence becomes an outlier, which is represented by the asterisk. The largest data was 54, the maximum, 54.63, and that's what this here is. With the box plot, you don't draw in the fence, which is why you don't have, I just put it in representing as a dotted line. So this would be a box plot that highlights outliers. They don't have to be. Most of the time, so this is a box plot highlighting outliers. Here is the same box plot not highlighting any outliers. So you just have the minimum, the Q1, Q2, Q3, and the max. By the way, when you see these box plots, and yes, if you're going to be dealing with statistical data, lots of studies have these, irrespective of what field it is, like astronomy or physics or chemistry or medicine, whatever. Sometimes they'll highlight the ends of the whisker with a vertical line by themselves. Sometimes they will be represented vertically as opposed to horizontally. Here's the final box plot. There's your box. There's your whiskers. There's Q1. There's your median. There's your Q3. There's your outlier. The box with the whisker, you're highlighting the outliers. Then the box and the whisker represents almost all the data. And then you highlight the outliers with an asterisk or a star or something. Using a box plot and quartiles to describe the shape of distribution. So if you had something that is right skewed, like in the first graph, notice you have this box and you have whiskers. The left one is fairly short and the right whisker is fairly long. And in each of these cases, the minimum does represent the end of the left whisker. The maximum does represent the end of the right whisker. If it's symmetric, then the whiskers are roughly equal distance or equal length, roughly. And if you look at the left skewed graph on the right, it's just the opposite of right skew. So the left whisker is fairly long compared to the right whisker. But also notice with the left skew, the median is fairly close to the Q3. And that kind of makes sense because you have most of the data is being clumped towards the right. And notice on the right skewed data, it's not as prominent, but the median is closer to Q1 than to Q3. So again, even in that regards, it's opposite. So if you arbitrarily didn't see the data, didn't see the classifications except on bar graph, if you came across a box plot and it's like it looked something like this, and it's like, oh, well, that's the min. Oh, that's the max. Oh, that's Q1, Q2, Q3. Oh, that min is that left whisker is fairly short compared to the right whisker, and that median is closer to Q1 than to Q3. So, holy cow, I'm willing to bet that this is right skewed. You look at a box plot, you can kind of estimate what kind of data set you're looking at. Is it symmetric, more or less? Is it right skewed, more or less? Left skew, more or less? Here, no outliers were interested. There was no interest in showing out. The whiskers are limited only by the minimum and maximum values. And with that, we get to the end of this section, but that also means the end of today's class.